All right, in this example, we are going to transform the absolute value function. So what that means is we'll take the parent function that we graphed in our last video, the most basic V shape you can get for your absolute value, and we are going to transform that. So that means you could stretch it or compress it. You could translate it. You could shift it to the left or shift it to the right. You could shift it up and you can shift it down. So let's take a look at just a couple of transformations and see how that affects our domain and range, some key features of our graph. So the first thing we're going to do is we're going to graph the parent function. F of x equals the absolute value of x. We have this table of values again, but we just filled this in the last video, so we'll save the time of doing the math. We can just take our work that we already did. We know that we're going to have the ordered pair negative 2, 2, negative 1, 1, 0, 0, 1, 1, and 2, 2. So we're just using our old work. That's perfectly fine to do. Let's plot those points. We have negative 2, positive 2, negative 1, 1, 0, 0, positive 1, and positive 2, 2. I'm going to graph. I know it's a V shape. It's going to go through those points. And then because we're going to graph another function on this same coordinate plane, I'm going to label this. That is our f of x function. So I'm just going to say, you know what? There's f of x. Maybe I'll even write absolute value of x just to remind myself what that function is. Okay, so we want to compare our f of x function with g of x. Again, that's the same thing as y equals. It's just a labeling system. We're going to have two functions, so if we called them both y equals, I'd say, hey, graph y equals, and you'd say, well, which one? There are two. So now we can just label. We can say you have your f function and your g function. So our g of x function is 2 times the absolute value of x. So we are going to do the math on this. What that's going to look like is we're going to plug these x values into the x of our function. So we're going to have 2 times the absolute value of negative 2. So first thing we'll do is take the absolute value of negative 2, which is a positive 2. So really we have 2 times 2, which is 4. So this ordered pair, the x value, the input was negative 2, and the y value is a positive 4. All right, we're going to do the same thing on the next problem, or the next input of negative 1. So 2 times the absolute value of negative 1, which means 2 times a positive 1, which is 2. So this ordered pair, the x value is a negative 1, and the y value is a 2. Now let's plug in a 0 for our x. So 2 times the absolute value of 0. Absolute value of 0 is just 0, so 2 times 0 gives us 0. Our input was 0, our output was 0, so there's our ordered pair. Now we're going to plug in a 1, so 2 times the absolute value of 1. Absolute value of 1 is just 1, so 2 times 1 is 2. So we have 1 for our input of x and 2 for our function value. And last, we're going to do 2 times the absolute value of 2, which is 2 times a positive 2, which gives us 4. So this ordered pair is 2, 4. All right, well, let's graph those points, and we can see how our g of x function compares to our f of x function. So, excuse me, so we have the ordered pair negative 2, 4. So from the origin, go 2 to the left and up 4 and plot that point. Then we have negative 1, positive 2. We have 0, 0. We have positive 1, positive 2. And then 2, 4. So what do we notice about our new g of x function? When we multiply the function by a 2 out front, did it change at all? Well, yeah, it did. It's a different graph, right? I'm not drawing over the same points we just did. So, all right, let's label that one g of x equals 2 times the absolute value of x. Okay, so the change that we made is we took our function and we multiplied it by a 2 out front. So that is, that's an a value. We just call it our a value is equal to 2. So if you're multiplying your absolute value function by a number greater than 1, this is a number greater than 1, we are going to stretch our v vertically. So if you take a look, you've got your V shape here, and then it got stretched vertically. So instead of being like this point was 1 away from the x-axis, now it's 2 away from the x-axis. This point over here was 2 away from the x-axis, now it's 4 away. So it got stretched up. That's why you get a more narrow graph, because we're stretching it. If that a value was a 3, it would stretch it even more. The higher your a value is, the more stretched your graph gets. Now, if your a value was between 0 and 1, if it was a fraction, that would be a compression, and it would flatten out. It would squish your absolute value, your v. You would have a v that's kind of going out where the sides are down here. That is what a compression might look like. So why don't we just make a little note of that this is a vertical stretch. That's the transformation we just did. All right, so let's compare our domain and range. So we just talked about the domain of our f of x function. I'm just going to write it over here. Our domain was all real numbers. And our range was, I'm just going to shorten our notation a little bit. Our range had all the y's greater than or equal to 0. Okay, so when we multiply our number out front by a positive 2, all it did was it stretched our v, so it made it a skinnier v. How does that affect your domain and your range? So your domain of your g of x function, well, it's still going to hit every single x value. You can input all of your x's and be okay, so it's still going to be all real numbers, so it did not change that. Now the range, is our range still y is greater than or equal to 0? So here's our function, the blue one. I can see it's hitting a 0, and all those output values are positive. It's never going to go negative down here if we're taking our parent function and multiplying it by a positive 2. So the range, all your y's are greater than or equal to 0. That didn't change. All right, so let's graph. What happens if we have a -1 multiplied by the absolute value of x? So these start to go a little bit faster. I'm trying to be detailed in the explanation so that we're understanding it, because you guys have not graphed these before. But we can run through this one a little faster. So we're going to plug in all these values for x. So we're going to do -1 times the absolute value of -2. Oops, it's not a parenthesis. Which is -1 times 2, which is a -2. So this ordered pair is -2, -2. Now we have a -1 times the absolute value of -1, which is -1 times a positive 1, which is -1. So our input was -1, our output was -1. Now we have -1 times the absolute value of 0. Absolute value of 0 is 0, so -1 times 0 is a 0, so we get input 0, output 0. All right, -1 times the absolute value of 1 is -1 times a positive 1. We input a -1, and we got back, if we multiply that, it is a -1. All right, -1 times the absolute value of 2 is -1 times a positive 2. -1 times 2 is -2, so the our input was a 2. Oh, I had that, yeah, okay. Blah. And our output is a -2. Did you guys catch that I wrote this input as a -1, but our x value is a positive 1? So sorry about that. That's a positive 1. I was trying to go fast, so this wasn't a super long video, and look at that, I made a mistake. Okay, so we're going to plot these points. We have -2, -2. We have -1, -1, 0, 0, 1, -1, 2, -2. So when you multiply your parent function by a -1, it did not stretch or compress. but here's our a value equals a -1. What do you notice about the graph? Well, it's not opening up like the normal V shape. Now it's actually opening down. So that's what we call a reflection. The V normally is up here, and it just got reflected across the x-axis, and now it's down here. That's what a negative a value will do to your function. We do want to identify the domain and range of this. So domain, you can input any x value, so your domain is all real numbers. But your range, well, what's our output this time? We're not getting positive y values like we were before. All of our outputs are negative. So this time, our range, all the y's are less than or equal to 0 because all of the output values we got were negative. Okay, so yes, it's a long video so far. Sorry. But let's just run through these last two. Without graphing, can we identify the domain and the range? So you have the absolute value of x, that's our V shape. What happens if we multiply it by 1/2? All that does is that's our a value equal to a 1/2. That is a compression. It's going to flatten your V shape, but it's not going to reflect it down, so your domain doesn't change. By the way, have you noticed our domain is all real numbers on all of these? I think it's pretty much going to be all real numbers for your absolute value function. But your range, because our a value is positive, that means that this V is going to open up. Maybe let's make a note. Opens up. That means our y values will all be positive, and it will include 0. So y is greater than or equal to 0. All right, our last example here, we have a -2 times the absolute value of x. So there's that number out front. Our a value is a -2. The negative is going to reflect it down. So this V is opening down like this. And that 2 is going to stretch it. It's going to be more narrow than the parent function. But how does that affect the domain and range? Domain is unaffected. Domain is still all real numbers. But your range is no longer positive values. If you're opening down, you're getting negative y values, not the positive y values up here. So your range is going to be all the y's that are less than or equal to 0. All right, way to hang in there to the end, guys. Nice job. I'm proud of you.